6.3, the conditional and circuits. Conditional is an if-then statement, and it's written like this. This says if P then Q, and we'll go back to this notation over and over again. So we have some examples here. If it rains, then I carry my umbrella. We can shorthand note this. If it rains, then I carry my umbrella. You got this arrow. If the president comes, then security will be tight. If the money doesn't arrive today, so let's say negate money, I will call to find out why. So the antecedent is the if part, and the consequent is the then part of the conditional. Example 0, symbolize the conditional statement, winners never quit. It gets a little bit difficult sometimes when you don't see the words if and then, and so I would maybe think of it with the terms if and then. So let's rewrite this with if and then. If you're a winner, then you never quit. Just thinking about it with the words if and then makes this problem a lot easier, I think, because sometimes it will be switched around backwards, but not in this case. Symbolize it. If you are a winner, then you never quit. How about that? If you're a winner, then you never quit. Number 1A. Suppose you got a 61 on the last test. Find the truth value of the following. If you got a C or higher on the test, then you will pass the course. This is kind of tough. You're going to think about this backwards probably. If you got a C or higher, then you will pass the test. Now think about what they said. We know that you got a 61 on the last test, which is not a C or higher. So you didn't get a C or higher on that last test. All right. Now, this does not mean that you're not going to pass the course, and that's what people are going to say. They're going to try to say that, oh, that means you didn't pass, but that's not what that means. Just because you bombed one test doesn't mean that you're not going to pass. We can't really tell anything here at this point. All right. So I don't know the truth value of this. The truth value of this, if we can't say that it's definitely false, then we just kind of default to it's true. Form a truth table for the statement given above. So we've got the statement of if C, then P. We've got two components. And remember how this works. If there are two components, then it's going to have 2 to the second power equals 4 rows. And how I like to do it is however many that is, 4 rows, half that many. You're going to have half that many trues in that first column. True, true, false, false. And then half that many trues in the next column. True, false. Let me line that up better. True, false, true, false. The statement was if C, then P. Now I'm gonna give a shortcut. Instead of copying C and copying P, since I've only got one thing to do here, I'm just gonna look at over here. This would say, true to true, right? True implies true. True implies true is true. And true implies false. True implies false. This is actually the only way to make it false. True implies false is false. And this is weird, but false implies true is going to be true. And the reason why, and false implies false is going to be true, is because what happens is if this part of the if-then statement doesn't apply, then we can't even say anything about that statement. And that's kind of what we have up here. All right. When this part is false, they didn't get a C or higher on that test, then the statement doesn't really apply. And so false, if this is false, then the conditional is going to be true. But here's our truth table. Here's the end result of the truth table. And what you need to take away is this row right here. That's the only time it's going to be false. True implies false is false. Everything else is going to be true. And that's kind of a main idea, a main takeaway of this lesson. Number 2, find the truth value of each of the following statements. If the earth is shaped like a cube, then elephants are smaller than mice. So that's a bizarre thing to say, right? So, true, false. Is that statement true or false? Well, is the earth shaped like a cube? Well, that part's false. And are elephants smaller than mice? That's false. And so, bizarrely, we have false implies false. But we just showed in that last truth table, false implies anything is going to be true. So the overall truth value of that overall statement, if the earth is shaped like a cube, then elephants are smaller than mice. Well, that statement's true. Part B, if the earth is shaped like a cube, then George Washington was the first president of the United States. Okay. Well, we just said the earth is not shaped like a cube, but what about the second part? George Washington was the first president of the United States. That's true. Once again, when that first part is false, we don't even really need to think about the whole statement. We can't really say that the statement's false. We don't know. Okay? We can't, well, I guess we do know. It's true because false implies true is true. In general, P implies Q is false only when P is true and Q is false. So again, we're talking about true implies false. True implies false. That's the only way to make the statement false. If the antecedent is false, that's P. That's the if part. This is true. And so what that's saying is false implies whatever. That's true. If the consequent is true, the consequence, the Q, the then part. If the consequence is true, that's like something implies true. That's always going to be true. So if the first part is false or the last part is true, either way, that's always going to be true. Write true or false for each statement. Here, T represents a true statement and F represents a false statement. True implies 6 equals 3 is false. So we've got a conditional that says true implies false. Well, that's the only way to make it false. True implies false is false. Part B, 5 is less than 2. Well, no, it's not. We have false implies false. False implies false is true. False implies false is true. Part C, 3 does not equal 2 plus 1. Well, yeah, it does. This statement would be false. False implies true. False implies true. Well, previous slide said false implies anything is going to be true. Number 4. Given that P, Q, and R are all false, find the truth value of the statement. So we can actually figure out if this statement right here, complicated as it looks, is true or false. So just plug them in. They're all 3 false. P, Q, and R are all false. So that means this is false implies not false, implies not false, implies false. all I did was just substitute F for false in place of P, Q, and R. And now I'm going to treat it like order of operations. Not false is true right here. So I have false implies true, which is true. And over here, I've got not false is true, implies false. True implies false is false. So now I go to this one. I've got this true implies false is false. That overall statement is false. Overall statement is false. Moving on, number 5, our favorite, truth tables. Construct a truth table for each statement. So I see two components, P and Q. That tells me there are going to be 4 rows. So I build my table having 4 rows. Half that many truths, half that many truths. The shortcut method of the table is just write it down. Copy down the statement. Not P implies not Q. And notice the rounded symbol. Sometimes we see it pointy and sometimes we see it rounded, but both of those mean and. Not P or not Q. Same thing. The rounded symbol means the same thing as the pointy symbol. They both mean or. Let me just double check I've got that written down right. Not P implies not Q, and not quantity P or not Q. All right. Not P, we're just going to negate the P column. That's going to be false, false, true, true. Not Q, we're going to negate the Q column. False, true, false, true. And then we can do the conditional. Conditional. False implies false is true. False implies true is true. True implies false is false. That's the only way it's going to be false. True implies true is true. Order of operations, you're looking inside the parentheses. So, like, I would just copy this. P is true, true, false, false, and not Q. Negate that. False, true, false, true. So this time we do the or statement. True or false is true. True or true is true. False or false is false. False or true is true. We're working this just like order of operations. Next thing we need to do is negate. We're going to negate that statement. So negate the one we just did. Not true is false. Not true is false. Not false is true. Not true is false. And finally, we can get to this, the and part of it. I've got true and false is false. True and false is false. False and true is false. True and false is false. So all 4 of them, all 4 possibilities are false. All right. Then we've got part B. Got P. We've got Q. P implies Q implies not P or Q. Try to build your table the same way every time. It doesn't really matter if you build it the same way every time, but as long as all of us build it the same way every time, we can compare our answers easily. If we were all mixed up, then it would be really difficult to have a conversation, I think. All right, so P implies Q. This first thing, I'm going to kind of cheat and just say, well, I can already see P and Q right there. So true implies true is true. And true implies false. This is kind of the big idea of today. This is where it's false. And false implies true is true, and false implies false is true. Over here, I'm going to do this negation, not P. Not P. I'm going to have false, false, true, true. I'm going to go ahead and copy the Q there. True, false, true, false. That was Q. Treating it like order of operations, we go inside the parentheses, we do this or statement. False or true is true. False or false is false. True or true is true. True or false is true. And then finally, I can get to the last part, the conditional. True or true is true. False, no, not or. True implies true is true. False implies false is true. True implies true is true. True implies true is true. So this one, all four of them are true. 5A, they were all false. 5B, they were all true. That doesn't always happen. But when it does, we have a special definition here. Contradiction is one that is always false, like this one. Something called a tautology, okay, you might try to pronounce that. Tautology is a statement that's always true, like this one. Always true, tautology. That word will come up at some point. So make sure when you see that word, you understand that it means every single situation is true. Now we can write a conditional as an or statement. Start off with your basic conditional, if P then Q. That is equivalent to the statement not P or Q. So get that down, make sure you can refer back to that. We can write it as either way. So then if I wanted to negate a conditional, we want the negation of the conditional. Well, let's just look at the same statement. You'd have, you'd have the negation of this. So that doesn't really do anything, but what we can do then is do De Morgan's law from last lesson. De Morgan's law is like, I call it like distribute and flip. We're going to distribute. Not P is P. Flip the symbol to and, not Q. P and not Q. So we used that first rule, and then we used De Morgan's over here. This was De Morgan's. Number 6, write the following conditional as an or statement. If this is your first time, we're glad you're here. You can put a then in there if you want. I don't know that helps at all. If this is your first time, then we're glad you're here. I think it really helps to symbolize. If this is your first time, then we're glad you're here. We want to write that as an or statement, so just use that rule. That rule says F implies G is equivalent to not F, or G. Just use that top rule right there. When you see a problem in words, a lot of the times you need to leave your answer in words. So let's put it back into words. I just use the symbols to help me see the equation or whatever, the equivalence. This would say, don't put the word if. It's not an if problem anymore, right? This is not your first time, or we're glad you're here. Some of these statements seem like silly things to say, and it doesn't really matter if it's a silly thing to say. It matters that we can apply the rules of logic. Now we want to write the negation of each statement. If you go to the left, then I'll go to the right. Okay, we don't really need that then in there, but whatever. If you go to the left, then I'll go to the right. We want to write the negation. So if we write the negation, it's going to turn into, I mean, it's this rule we see at the top. So, you know, you could say, well, that's equal to not L or R. I think it's easier to look at the one at the top. Not P or Q, not L or R with the negation. And then we can use De Morgan's to distribute and flip. L and not R. L and not R. You go left and I don't go right. There are other ways to word that, but that's pretty close. Part B, it must be alive if it is breathing. Sometimes it's a little bit difficult to see it if it's out of order, but think about it as if it is breathing, then it's alive. I think it's very useful to put it in order, in that order, in if-then order, instead of backwards. Even though they mean the same thing, I just think it's easier to think about that way. If it's breathing, then it's alive. We're trying to negate that. We want to negate that statement. So can you jump? Can you jump to this? Breathing and not alive? That kind of hurts my brain a little bit to think about it. So maybe if you need to go through that top step first, change the conditional to not P or Q. Change the conditional to not B or A. And negate that, if that helps. And then distribute and use De Morgan's as B and not A. If that helps, if you need to do that extra step, do that extra step. Because it is kind of difficult sometimes, I think, to think about. So what does that mean? B, it is breathing and not alive. Yikes. But that's what it says. Okay. One important application of logic is circuit design. And if anybody's ever designed circuits in one of your classes, your engineering classes, or any kind of electronics, you're looking at circuits, and circuits follow a certain kind of logic. So like this symbol right here is a switch, and we're just going to call that switch P. Okay, so there's your switch is open right now, and current can't get through for your circuit. A series circuit, think about it. In order for the current to get through, both P and Q would have to be closed. So that is a picture of P and Q. And then a parallel circuit, think about how the electricity can get from here to here, the current can get from there to there if either P or Q would be closed. So that parallel circuit is a picture of P or Q. And so we can, sometimes I'm not very good at circuits, but sometimes we need a parallel circuit and sometimes we need a series circuit. Number 8. And these questions, I think I put the cart before the horse a little bit. We should be able to just write what we see. But as far as simplifying, we're going to need some rules that I put on the next page. So it's a little bit out of order, I think. But when I look at this problem, I see an or right here, and I see an and. And so I see P or Q. And not Q. That's what the circuit says. Now, it may be possible to simplify these. Let's come back to the simplification part. I see an and right here. I see an and right here, but I also see an or. This problem to me looks like P and Q or P and R. Okay, so we look at the next one. You're going to have to do Q and some stuff. But then you can see a decision here. You got to do one or the other. And then you're going to see an and here. Start with Q. And you're going to need to do Q and not P or P. Whoops, I shouldn't have written the word or. Symbols. Q and not P or P. All right, so writing the circuit isn't that hard. I think simplifying the circuit's a little bit harder because you end up needing a lot of these rules. And some of these rules we've talked about, like De Morgan's. De Morgan's laws we've talked about. But some of the other ones we haven't. And so it's a little bit tough to use these sometimes. And so let's see if we can't give it a go. All right, look at this one first, 3B, and we're going to end up using 11B at some point. Where's 11B? 11B. Okay. So anyway, let's check it out. All right, so 3B, it's kind of almost like distributive property. It's like I can take, you can kind of look at it as distributing that not Q. I'd have P and not Q if I distribute, or this or right here, Q and not Q. That's rule 3B. 3B was a distributive law. Basically, I just distributed. Okay. Now, if you notice over here, you've got Q and not Q. Q and not Q. So like that has to be true. Like whether it is or it isn't, whether the switch is closed or it's not, it's still gonna I mean one or the other. It has to be true. And I said that was number 11B. If we look down here at 11B, all the way down at the bottom, P and not P is, oh, it was an and problem? Oh, shoot. It's false. Okay, sorry. That's false. I said true, that's false, because, and that should make sense, because it can't be both at the same time. So this right here is false. And so what we've got then, like I said, this is tricky. I already screwed it up. Okay. We've got whatever this says, P and not Q, or something that we know is false. It has to be false. Well, in order for this to be true, in order for this circuit to work, this part would have to be true. This part would have to be true. But that's what we're left with. P and not Q. All right, so then we look at the other one. We look at this other one. And we're going to use 3B again, but we're going to use it in the opposite direction. It's more like a GCF. See how they both have a P in it? Okay, they both have a P and in it. It's like using 3B, but using it the reverse direction. They both have a P and, so we're kind of just taking this out like it's a GCF problem from algebra class. If we take that out, what would we be left with? Q or R. P and Q or R. So what, like this one, I guess it'd be nice to simplify the diagram. I could redraw this diagram and say, well, here's P, and then I could go with Q or R. That says P and Q or R. It's a simpler way of drawing the diagram. And as an electrician, you might want to draw a simpler diagram because you're going to save money on parts. You don't need two of those P switches. You can just use one. This one we changed to P and not Q. P and not Q. If you think about it, think about current trying to travel through this circuit. Well, if this is open, then this one's going to be closed. And if this one's closed, then this one's going to be open. It's never going to go this way. So we can simplify it and just say P and not Q. That's a P. All right, last one. All right, so what do I use? I guess I used that same 3B again right here, and think about this as distributive property. I can distribute that, and so I've got Q or P. We've got Q or P, and right here, not P or P. Now this is what I tried to do earlier, but not P or P. Think about it. Not P or P has to be true. One way or the other, you're going to get that. That is true. Either it is or it isn't. That's true. So I know that this is overall, that part is true. Well, in order for something, in order for two things anded together to be true, then they both have to be true. But all that does is that means that I don't need that part. I can just say that's Q or P right there. I've got Q and Q or P. This is going to be property 6B or 6B. This. So using that rule 6b, we can simplify all of that to just